All right, this video is specifically for Abby and Emmalee. Emmalee wanted the last box on quiz 5. That's going to be this with quadratic formula. And then Abby wanted to go over quiz 6 specifically. So I'm going to start with the last box on quiz 5. This is 13.3.1, 13.4.1. This is all quadratic formula stuff. So just as a note, this is the quadratic formula. I'll write it up here. This is a formula that gives you the roots of a quadratic equation, meaning it tells you what x needs to be to make any of these quadratic equations equal 0. So it answers a question like this. So x is going to be negative b plus or minus the square root of b squared minus 4ac all over 2a. And a, b, and c come from the standard form of our quadratic. So it's not the completed the square form, it's the standard form. And for instance, it'll look like this. Y equals ax squared plus bx plus c. So a is our coefficient of our quadratic term, b is our coefficient of our linear term, and c is our constant. And as I said before, it's telling us when we're going to get our zeros, right? When the function will equal 0. So for this first one, we already have it set up to equal 0. So when it's in this form, we can use quadratic formula, and it is. So a is going to be 1, not x squared. Remember, it's the coefficient, so it's a 1. A is 1. B is going to be 7, and c is going to be 3. This will be different for this one because, again, it's not solved for 0, but we'll get to that in a second. So if I just plug these into the formula, negative version of b means I have negative 7. Plus or minus the square root of b squared. Well, b squared is 49. Minus 4 times whatever a is times whatever c is. A, of course, is 1. C for our problem is 3. And then we're going to divide by double a, twice a. So if a is 1, 1 times 2 is 2. And that's what x is going to equal when we want this to equal 0. And that's what we're asking here, right? What's going to zero this out? What number do I plug in to make this equal 0? So for this, we just simplify as much as we can. Technically, this is your answer, right? This is kind of like saying your answer is 3 plus 4 when the answer is really 7, right? We just haven't simplified it enough, which for me doesn't matter a ton. But to make this useful for later problems, you might want to learn how to simplify. So I'll show you that. 49 minus 4 times 1 times 3. Well, that's just 12. So 49 minus 12 is going to get us 37. So we have the root of 37, so close to being a perfect square. So it's a little bit more than 6. Plus or minus negative 7, all over 2. 37 is a prime number, so we can't simplify that any further. We can't divide both by 2, and obviously, because this isn't a root, you can't divide that by 2 anyway. So we're just going to circle this. That's what x is. You could have found this answer by completing the square, just like we would have done in a problem up here. But quadratic formula gets it done this way. This next one, if we rearrange it so it is solved for 0 by subtracting 5 from both sides, we can more clearly see what a, b, and c are. A is 1, b is negative 4, and it looks like c is negative 5. Hold on 1 second. Get a phone call. There we go. So using these, we can plug it in. B is negative 4. So when we plug in the opposite of b, right, that's what this is, negative version of b. So if we negate negative 4, we get positive 4. And we have plus or minus b squared. That's going to be positive 16 minus 4 times a times c all over double a. And this one, double a is just 2. So 16 plus 20 is going to get us 36. Hey, that's nice. And we're supposed to be able to divide both of these by 2, right? Otherwise, we have to stop. Well, we know 36, the root of that is plus or minus 6. So we can either divide both now, or we can simplify, or we can add or subtract this and create 2 answers. I'm going to divide both now and get 2 plus or minus 3. So if we do 2 plus 3, we get 5. If we do 2 minus 3, we get negative 1. So we get 2 different answers for x. Either of these would work and zero this whole thing out. 5 or negative 1. And we can check that very quickly. If I plug in negative 1, I get 1. Here I'd get 4. 1 plus 4 is 5. If I plug in 5, I get 25 minus 20. That's also 5. So these are solutions to our equation. They'd also work if I set this equal to 0. This one is definitely not in standard form, but if we rearrange it a little bit, we can get it there. I'm going to actually add the t squared over here. So I'm going to get a t squared. I'm going to subtract 2 t's and get 6 t's. And of course, I've already got a minus 9 there. Since I moved everything over by adding this and subtracting that, I have 0 left, which is what I wanted. So it looks like A is going to be 1, B is going to be 6, and C is going to be negative 9. So if we apply this to our quadratic formula, and I'll do it in a different color so you can tell I'm working on this one, not this stuff. X is going to equal the opposite of B, plus or minus the square root of B squared, which is 36, minus 4 times A, and our C value is negative 9 this time, all over double A, which in this case, again, is 2. But if A were like 7, we divide by 14. So 36 plus 37, or not 37, 36 here is going to get a 72. So this is root 72, which is not a nice root. If you wanted to simplify that, though, remembering a little bit from shapes class, perhaps, root 72 can be rewritten. So here's root 72, and I think you would agree with me that root 72 is just 2 times 36. I mean, that's kind of where we got it from, right? 36 plus 36. Well, that can be written as 2 times 18, and that can be rewritten as 2 squared, because that's what that is, times 2 times 9. And that can be rewritten as 2 squared times 2 times 3 squared, because that's what 9 is, right? Now, you don't have to show all these steps, but this is just me going slowly, taking out one number at a time. Now I've got all prime numbers here. This is our prime factorization of 72, actually. It's 2 cubed, 3 squared. But I left it as 2 squared and 3 squared because remember, when we have multiplication inside here, we can root individually. So if we root 2 squared, we just get 2. And if we root 3 squared, we just get 3. And on the outside, it'll be 2 times 3. On the inside, it'll just be that 2 that we could not root. So in other words, root 72 is the same thing as 6 times root 2. It's interesting. Well, if I rewrite that, then I've got this. I've got x is going to equal negative 6 plus or minus 6 root 2 all over 2. Now remember, this is 6 times root 2, so we can't just add these right here and get rid of 6's somehow. That's not going to work. But we can divide these both by 2 and get x equals negative 3 plus or minus 3 root 2's. We had 6 root 2's, we divide it in half, we get 3 root 2's. So this is as simple as we can get for our answer. To be honest, I would accept something like this very easily. After you've simplified what's inside here, I think that gives you a good idea what's going on. If we got a negative inside here, we'd have imaginary numbers, so it's good to figure out what's going on here, and then after that, we've got a good enough answer. But if you want to be super persnickety, there you go. That's the most simplified form. I'm doing that in parentheses. The last one. It's using quadratic formula in a clever way. So here's our quadratic. You'll notice it is in standard form. A is 1, so that's useful to know. I'll write that down. A is 1. B and C we don't know. But we do know that one root of this is this. So remember what the quadratic formula does. It tells us the roots. In other words, the number for x that makes it equal 0, right? So if you do this, you get a root. Well, apparently this is one of the roots that we got when we did this. So in other words, I know all of that is equal to 8 minus root 7. After I plugged in A, B, and C, which I don't know what they are, apparently I got this, right? Well, if you think about it, the only way I could have gotten 8 was from here. So that means 8 is going to be equal to negative b over 2a. So I'll write that down. That's where we're getting the 8 from. And of course, we're dividing both by 2a. So this minus root 7 must have come from here. So in other words, the root of b squared minus 4ac all over 2a must equal the root of 7. So knowing this, we know a is 1. So let me just scratch this out. 2 times 1, of course, is just 2. This is just 1. That's just 1. Let me cross that out. Let's zoom in for a second. So if I know that negative b over 2 equals 8, well, I can figure out what b is. If If I times both sides by 2, negative b would equal positive 16. So that means regular b equals negative 16. So our b value must be negative 16. Again, if I plug in negative 16 and negate it, I get positive 16. 16 divided by 2 is 8. So b is negative 16. Over here, figuring out what c is going to be interesting, but not too bad. We know b is negative 16 now. So I'm going to do a little bit of work down here. I know that the root of b squared, and remember b is negative 16, minus 4 times a, and a is 1, so that's just 4, times c, should equal, divided by 2a, which is just 2 because a is 1, should equal our root 7. Well, using this idea of simplifying roots, do you see how if there's a 2 on the outside, there must have been a group of 2's on the inside? And if there's a 3 on the outside, there must have been a group of 3's on the inside, right? We can reverse engineer, take this back to that. Well, what I'm going to do is I'm going to times both sides by 2. And that's going to get me, this right here is 256. And if I times by 2, that gets rid of the division, and I get 2 root 7's. And this is where this idea comes in, right? If there's a 2 on the outside, we could put it back in with 2 2's on the inside. And that's what I'm going to do here. I'm going to say that the root of 256 minus 4c must equal the root of 2 2's on the inside times 7. This and this are equivalent. So this is really 4 times 7. So that's 48 inside the root. So what's inside this root must equal 48. So in other words, I know this. 256 minus 4c must equal 48. Now the question is, what do I subtract from 256 to get 48? Well, it turns out that all of this, whatever 4c is, needs to be 228. Wait, 48. Hold on. 4 times 7 is 28. There we go. Now we're talking. Sorry, I'm a little bit on autopilot right now. 4 times 7 is 28. So 256 minus 228 is going to give us 28. And the 28s are a coincidence here. That's kind of why I remembered I must have goofed. 256 minus 228 does give us 28. So the question is, what times 4 gets us 228? Well, 4 times 50 gets us 200, right? And 4 times 7 would get us 28, right? So in other words, I need 57 times 4 to get there. So that's what c is going to equal. So c is going to equal 57. Because when I take 57 and times it by 4, I get 228. 256 minus 228 is 28. So this one's a little bit more thinking outside the box, but let's just back up and go over it again. We understand quadratic formula. It's this thing, right? It gets us our answer for x when our quadratic equals 0. So when our quadratic equals 0, we just plug in our values, 1, 7, and 3, right, from standard form. Simplify it down. If it doesn't equal 0, you move things around. If it doesn't equal 0, you move things around. Quadratic formula tells us where our roots are. So if I know my root for one of my roots is 8 minus root 7, then that means that this part right here must be equal to 8, because that's everything that's not in the root. And this part right here, including the 2a, must equal root 7. In this problem, we knew that a was 1. So instead of negative b over 2a equaling 8, I just know negative b over 2 equals 8. So what number do I divide by 2 to get 8? Well, 16. But of course, I'm going to negate it, right? So I need negative 16. Once I know that, I can fill in some blanks over here and set that equal to root 7. Using the idea of simplifying roots, I can times by 2 and then put that 2 back in the root, revealing that this is 28, not 48. So this stuff inside must equal 28. And I deduce that 228 is the number I need here. So how do I get it? 57 times 4. That's the last checkbox for quiz 5, basic. Last one's a bit of a doozy. Quiz 6, let's talk about it. So quiz 6 is all about parabolas and circles and graphing them. This is a parabola. There we go. This is a parabola because x is squared but y is not. That's going to be a circle if we have x and y squared, at least in this class. So to graph this, we know it's going to open upward because we have a positive 1 in front of here. And because it's positive, it'll open up. One way to think about this is as I plug in more numbers for x, whether they're negative or positive, this is going to grow very quickly because it's getting squared, right? Already, if I plug in the number 5, I'm getting a 25 here, right? And there's a 30 minus 5. So 25 plus 25 is getting me 50, right? It's just going to grow very quickly, and I can make it as big as I want. So there will be a bottom to this parabola, and that bottom will be our vertex. And to find that point, to figure out when this is the smallest it can be, because that's what this point represents, right? There's the y-axis and the x-axis, right? We want to minimize y to find the bottom, so we want to make this as small as possible. And trying to figure that out is difficult, right? We can plug in negative numbers, but remember, negative numbers are going to be positive when we plug them in here. So just plugging in negative numbers might not get you your vertex. You might get some other random points, but you won't know for sure. So all this to say is that what we need to do is we need to get to this form where it's easy to tell where the bottom of this is. The way we're going to do that is by completing the square. We know how to do that. This part right here gives me a clue that I should make a perfect square of x plus 3. Now, this is not what this equals, right? Because if we distribute this out, we're going to get x squared. We're going to get a 3x and another 3x. That gets me my 6x's, right? That's why I knew I needed a 3 there. But it's also going to get 3 times 3. And that's 9. And that ain't negative 5. So we can do this little algebra trick to add 9 to this side so that all of that is this. Now we still have this minus 5. And of course, just adding 9 to this side would change the problem. But if I add 9 to both sides, it won't. So this is the same problem as before. It's just now I've got it in a perfect square, which is why we call it completing the square. If I subtract 9 from both sides, then I'll get y equals the quantity of x plus 3 squared, and that'll be minus 14. So in this form, I can clearly see what's going to make this as small as possible. Notice that this part right here can never go negative if we're using real numbers, right? No matter what I plug in, even negative 7 gets me negative 4 overall, right? Negative 7 plus 3 gets me negative 4. Well, that negative 4 will get squared and become 16, right? So I can never make this negative. The smallest I can make it, and remember, I want the smallest because I'm trying to find the bottom here. The smallest I can make this is 0. And the way I would do that is by plugging in negative 3 for x. When I do that, I'll get 0 here. And so the thing I have control over has been made small as possible. And the thing I don't have control over is just going to happen. So we got 0 here, minus 14 gets us negative 14. So it looks like when I plug in negative 3, I get the smallest value for y, which is going to be negative 14. So this is our vertex. It's the bottom of our parabola. It's what makes y the smallest. When x is negative 3, we get the smallest value possible for y. Any other number than negative 3 is going to make something positive here, which is going to make the negative 14 less negative, right? It's going to make it like negative 13 or negative 12 or 10. And that's going to make y higher, which will give us points around our vertex. But we want the lowest possible, which is going to be when this is 0. So our vertex is at negative 3, negative 14. That's over here. Negative 3, and this graph goes down to negative 16. So I know that's negative 14. So there's my vertex, and it's going to open upward. Now, this has an a value in the front of 1, right? Talking about like our standard form, right? A is 1, B is 6, C is negative 5. A is 1, which tells us it's going up because it's positive. And it's also going at a normal rate. So the 6 and the negative 5 right here really only kind of adjust where our parabola starts for our vertex. How quickly it grows and in what direction is really determined by this guy. So this will grow the same way as this, right? The 6 and the negative 5 just kind of move that around. They're going to grow the same, right? They're identical if I remove the 6 and the negative 5. So how does this one grow? We call this the parent function because it's really easy to figure out how it grows. When I plug in values like 1 for x, I would get 1 squared, which is 1 for y. If I plug in values like 2, I'd get 4. 3, of course, is going to get me 9 when I square it. So our normal function would start at the origin, and it would go over 1, up 1, and there would be dots on either side. It'd go over 2, up 4, dots on either side. Over 3, up 9, dots on either side. Well, ours is the same parabola. It's just moved down here. So when we plot our new points, and we know it's going to be symmetrical, we're going to go right 1, up 1. And of course, making it symmetrical. Because 1 gets 1. So 1 to the right and 1 up. The next one we would get is 2 gets 4. So when I go 2 to the right from my vertex, I go 4 up. So 2 to the right from my vertex goes 4 up. If I go 3 to the right from my vertex, I should go 9 up. So 3 to the right is going to go 9 up. So here's 4, 5, 6, 7, 8, 9. And there's our parabola. After you've got a few points down like this, I think it's totally fine to draw your parabola. If you've got room for more of these obvious points, you should definitely include them. 2 dots on either side really isn't enough to get an idea of what's going on. But after you've got 3 dots on either side, you definitely don't need to go any further. I can't imagine any other teachers asking you to do more, so I won't. So these coordinates are points on this equation. This is the coordinate 0, 1, 2, 3, 4, 5. And that means if I were to plug in 0 to my equation, either this or this, doesn't matter, they're both the same thing, just different ways of looking at it, I should get -5 for y. And that makes sense, right? If I plug in 0 for x squared and 0 for x, those are both zeros. 0 plus 0 minus 5 is -5. So yeah. You could always plug in numbers to the right or left of -3, like -2 or -4, right? Because -3 is where this guy is. But it's much easier to choose the parent function to graph on either side. Looking at the next basic question, it looks very similar to the last one we did. It's going to go upward because we have a positive value for a, but it's going to go up 3 times faster. What I mean by that is instead of going up like our last one did, our parent function like this, 1 gets 1, 2 gets 4, 3 gets 9, it's going to go up twice as fast. So y equals 3x squared is really what it's going to work like. That means 1's not going to get just 1, because 1 squared is 1, right? But then I times it by 3 and get 3. 2 squared is 4. 4 times 3 is 12. You see how this is 3 times bigger for each of these? So 3 is going to get us 27, because 9 times 3 is 27. And that's what happens when you plug this in. 3 times 3 is 9, times 3 again is 27. So it's going to grow 3 times faster in the upwards direction. So to figure out where our vertex is, the bottom of our parabola, because again it's opening upward, so we're going to have a bottom to it, we need to complete the square. So the way we'll do that is we're going to get rid of the a value in front of here. And we're going to do that by dividing everything by 3. When we do that, we get a weird fraction over here, but it'll be okay. This allows us to easily complete the square. So I know I'm going to need x plus 1 quantity squared, because that'll get me my x squared and my 2x's. But it will also get me 1 times 1, right, when I expand this out. And that's not here. 1 times 1 isn't here, because 1 times 1 is 1. But if we add that 1 to here, then that is what's in the purple. Of course, to do that, we have to add 1 to both sides, otherwise we've changed the problem. And we'll get plus 4/3 over here equals y over 3 plus 1. Cool. So now that we've figured out what our square needs to be, we don't need that 3 gone anymore. I moved the 3 so I could figure out what the complete the square would be. So if I just times everything by 3, and then subtract 3, oh, that's a 4 now. 4/3 times 3 is 4. And then subtract 3, we've got our completed square and our vertex formed. So remember, we want to find the bottom. So what's going to make this as small as possible? Well, if you notice, because we're taking a positive times a positive, because this will always come out positive, we're using real numbers, this will always be positive or 0. The lowest we can get it is 0. So what's going to make this 0? Well, when x is -1, we'll get 0 here. 0 squared times 3 is going to be 0. But of course, when this is all 0, we don't get 0 for y. We get 0 here, and then we add this 1. So y is going to be 1 when we plug in -1 for x. That is going to be our vertex. That's the smallest we can make y. And the way we do it is by plugging in -1 for x, and that'll minimize this, and then we get a plus 1, because we're always going to get that, and that'll give us y. So our vertex is at -1, 1, and it's going to grow 3 times faster in the up direction. So I'll plot that like this. And if I graph it, normally 1 to the right and 1 up is what I get. But here it's going to grow 3 times faster. So 1 to the right isn't going to get 1. 1's going to get 3. And of course, it's symmetrical. If I go 2 to the right, normally I get 4. But here I'm going to go up 3 times as fast. So instead of 2 getting 4, 2's going to get 12. 4, 5, 6, 7, 8, 9, 10, 11, 12. Off the screen. Pull that back down. And of course, 3 would get 9 normally, but if here it's going to grow up 3 times faster. 3 is going to get 27, which I don't have room to do, so I'll just draw my parabola with 2 dots on either side. So the only difference between this and the last one is that completing the square is a little bit trickier. Right? We're going to have to divide everything by 3 first. After we get the square completed, and just put it all back. Get y on its own. Our vertex is still going to be -1, what makes this part 0, comma 1, because that's what's left over. And it's just going to go up 3 times faster. So instead of 1, 1, it'll be 1, 3. Instead of 2, 4, it'll be 2, 12. And instead of 3, 9, we're going to get 3, 27. And if we run out of room, we run out of room. The good news about this one is that it's already got the square completed for us. So this is a going to give us our vertex for our parabola. Same thing here. You'll notice that this one is y equals, so when we minimize this, we're minimizing y. And it's going to go downward, right? It's got a negative in front of here. And it's going to go down twice as fast as a normal parabola. So this one's going down, and it's going to go down twice as fast. Our vertex for this one is going to be -1, because that's what, or sorry, not -1, +1, because that's what's going to make this 0. 1 minus 1 is 0. 0 squared is 0. 0 times -2 is still 0. And of course, what will be left over is 0 minus 6, and that'll give us y. So 0 minus 6 is -6. So when I plug in 1 for x, I get -6 for y. That'll be our vertex for this parabola. So let's graph that quickly. 1, -6 is here. 1, 2, 3, 4, 5, 6. And it's going down, so I shouldn't put a line there. There we go, 1, -6. It's going down twice as fast as a normal parabola. So instead of going 1, 1, it's going to go 1, 2. Because 1 squared is 1 normally, but then we're going to times it by 2, because it's going to go down twice as fast. 2 squared is normally 4, so we would normally go 2, 4. But it's going to go down twice as fast, so 2 is not going to get 4, 2 is going to get 8. 2, 4, 6, 8. I think I did that right. 2, 4, 6, 8. There we go. And of course, it's symmetrical. Now I'm running out of room. 3 would normally get 9. It's going to get 18, but I don't have room for that. So I'll just draw my parabola like this. For our next parabola, you'll notice that it's x equals. So we're minimizing x. It's going to either open to the right or the left, because we're changing how far to the left or right we go. That's what x is, right? Minimizing it or maximizing it. It's opening to the right. So in other words, it's opening like this. So we need to find the smallest we can make x. And be careful. When I plug in 1 to this, yes, this gets me 0. But what am I plugging in for? I'm plugging in for y. So when I plug in 1 for y, not x, 1 for y, I'll get 0. 0 squared is 0. 0 times 2 is still 0. 0 minus 6 gets me my x. 0 minus 6, of course, is -6. Now, will they always be flipped like this? No. But I set it up for this particular problem to mostly behave that way. How it'll be tomorrow is anybody's guess. Again, use your brain. Actually walk yourself through it. Don't just assume they'll be flipped. So if we want to graph this one, it's going to go to the right twice as fast as a normal parabola. And it's going to start at -6, 1. 1, 2, 3, 4, 5, 6, 1. Going to the right twice as fast means that instead of going up 1 over 1, we're going to go up 1 over 2, because again, we're heading in the right direction. We're going this way, and it's going to be symmetrical. Instead of going up 1 over, or up 2 over 4, because 2 squared is 4, we're going to head up 2 and go 8 to the right, because we're moving twice as fast. Again, twice as fast because of the 2 in front of here. So 2 doesn't get 4, 2 is going to get 8. So here's 4, 5, 6, 7, 8. And of course, it's symmetrical. If we go up 3, we'd normally get 9, but it's going to move twice as fast. So 3 is not going to get us 9, it's going to get us 18. So here's 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And I could keep going if I wanted. Up 4 would get us 16 normally. 4 squared is 16. Twice as fast as 32, I'm going to run out of room. And of course, 3 dots on either side is, I think, plenty. So there are our parabolas. If we zoom out and we ask the question, how are the graphs related? Well, these are the exact same parabolas. They move at the same rate, twice as fast. Their locations are just different, and they're rotated. And that's the big thing. If we take this one and rotate it 90 degrees counterclockwise, we'd get the other one. They're the exact same parabola. And there's something about switching your x and y's from last year that we talked about. And by we, I mean you and Mrs. Block, right? Talked about switching x's and y's to like a 90-degree rotation. And that's kind of what's going on here. You don't have to memorize that X and Y switch means 90-degree rotation, right? You can just think about it. But that is the connection to last year. The last basic problem we have is about circles. And you can tell this is a circle because we have x squared and y squared, not just one or the other. You can also tell it's a circle and not like an ellipse or some kind of egg shape because the numbers in front of our x squared and y squared, the coefficients of our quadratic terms, are the same. If there was like a 5 in front of this and a 3 in front of that, that would stretch our shape weirdly, and so we wouldn't get an exact circle. We'd get some kind of ellipse. Now, one of the things I like to do when I'm teaching this is to group my x terms together and my y terms together, just to make it a little bit clearer. Because if I were to show you a problem like this, without any of the y stuff, you'd probably think this is a parabola, right? And we could complete the square to find the vertex. Same thing if I covered this up, you'd probably think this is a parabola, and we could complete the square to find the vertex. Well, it's not a parabola, it's a circle, but we can complete the square twice to find the center of our circle. So if I complete the square here, I'm going to need x minus 2 quantity squared to get me my x squared and minus 4x, but it's also going to produce negative 2 times negative 2, which I don't have here. That's 4. So all of this is inside of here. And of course, if I'm going to add 4 to this side, I have to add 4 to that side, otherwise I've changed the problem. Over here, I could complete the square by adding 5 to y and squaring it. That's our perfect square here. And of course, this is going to produce y squared and 10y, right? Y times 5 and y times 5 adds together to 10y, but it's also going to do 5 times 5. And 5 times 5 is 25. So that's not there. I need to add that, otherwise this wouldn't equal that. But now it does. But of course, adding that 25 would change the problem if I don't add it to both sides. So what we end up with is this. X minus 2 quantity squared plus y plus 5 quantity squared equals, and this to me looks like we're getting 50 plus 20, that's 70, plus 4 is 74. So in this form, we can easily see what our center is going to be. Now, to discuss why this gives us our center, this is really distance formula, which is really Pythagorean theorem. Pythagorean theorem says that the distance between these 2 points is basically a right triangle. And that right triangle has a side of A, a side of B, and a side of C. And the distance between those 2 points you could find by squaring A, squaring B, adding them, and using Pythagorean theorem to figure out C squared. Of course, this gives us C squared and not C, and we want to know the distance, which is C. So this would give us C. So you'll notice that what we have here is similar to the top part Pythagorean theorem. We have something squared plus something squared equals apparently something squared. And the distance between our points is this, right? The root of this, right? Not C squared, but the root of this would be our distance. So let's talk about what this means. This means the distance between any point and this point. Negative 2 and 5 does tell us a point. We'll talk about that in a second. So that's some point, and this is any other point, is always going to be a distance of root 74. Not 74, because that's C squared, right? But root 74 away. So if I go root 74 away from this dot, and I do that in every possible direction, and if I do that again and again and again, and again, I think you'll see that if it's always the same distance, again, the distance between any point, and our center point will always be the root of 74. Well, if the distance is always the same between any point and our center, we'll end up with a circle, right? They'll all be the same distance away. So if we set this equal to 0 instead of 74, it's telling us the distance between our center and any point would be 0. So the distance between our center and any point is 0. Well, that would, if there's 0 distance between our center and another point, well, then the center must be that point, right? What point is 0 distance away from this? This point, right? Only itself is 0 distance away. So if I can figure out where to make this 0, I found a distance of 0 away from my center. In other words, I found the center. I know it sounds like a lot, but basically what I need to do is make this 0. So when is this going to be 0? When x is 2. And when will this be 0? When y is negative 5. This will be our center. If you were to plug those values in for x and y, you get 0 here. 0 squared plus 0 squared is 0. It doesn't equal 74, which makes sense. It shouldn't be a true statement because, remember, this isn't on our circle. Our circle is this. Finding where it equals 0 just gives us that center point. So now we have our center, and we know that our radius, the distance from all of these, is, again, not 74, because that's c squared. Something squared plus something squared equals something squared, right? We want c, the distance. So we need root of 74. If only that were a 64, because the root of 64 would be 8. 74 is 8 and change, but we can still graph this. So if I look to graph center at 2, negative 5, I know my graph's a little bleed through right now. Our paper that we're using for the end of the year is not very high quality. 2, negative 5 is 1, 2, 3, 4, 5. That's our center at 2, negative 5. Let me zoom in. And we know that if we go root 74 in every direction, we'll get an idea of what our circle looks like, right? That's our radius, root 74. Remember, root 74 is 8 and change. So if I go up 1, 2, 3, 4, 5, 6, 7, 8 and change, and we'll call that 8 and change, then I've got another point on my circle. Same thing if I go to the right 8 and change. 1, 2, 3, 4, 5, 6, 7, 8 and change. And the left 8 and change. 1, 2, 3, 4, 5, 6, 7, 8 and change. If I go down 8 and change, 1, 2, 3, 4, 5, 6, 7, 8 and change, I'll get another point. Now, we do need to label these points about where they are. You'll notice that this point is 2 to the right from our origin. So it's still 2 for x. And that makes sense, because between these 2 points, I didn't move left or right, so the x value wouldn't change. But I did move up. So right in here, I need to write negative 5, and then I went up 8 and change, or root 74 to be exact. So whatever negative 5 plus root 74 is, that's our new y location. And of course, negative 5 plus 8 and change is like 3 and change. And if you look, 2, 1, 2, 3 and change is where we ended up. Using the same logic, if I go down, I haven't gone left or right, so my 2 stays the same. But I've gone down from negative 5, the number I had here. I went down 8 and change, also known as root 74. Well, 8 and change away from 5 is like 13 and change. And if you look, this is 13 and change, because there's 14, 15, 16. There's 13 and change. This is the exact location of where it is. 13 and change, of course, is just an estimate. Here, I'm moving to the right. So I'm going to go from 2 and add 8 and change, right? So that's 2 plus root 74. That location right there is there. And of course, we didn't move up or down, so our y value would not change. It's still negative 5. From our center, if we move left, we've got 2 minus root 74. And of course, we didn't move up or down, so it's negative 5 here. And now's the time where we get to draw our circle. And I'll make this one sort of nice. Not 100% nice, but sort of nice. So backing it up, we need to find the center, and the way to do that is to complete the square. Make sure when you complete the square, you add stuff to both sides, so you can see what your radius will be. Your radius will not be 74. Your radius will be root 74, or whatever the root of this number is. Our center is whatever makes this 0. When we graph this, if you get a nice number, you can just label your points very easily, but if you don't get a nice number, that's okay. You can just add on in the direction that you're going, or subtract in the direction you're going, depending on which. We're going to look at some intermediates. There's quite a few. But if you really understand this stuff, it shouldn't be too bad. And if you don't, it's going to be a bit of a challenge, but that's okay. Unfortunately, learning takes time, and we're running out of that, but it's still going to be all right. 14.1.3. Notice it starts with x equals. So this is a parabola, and it's going to either move right or left, because we're going to minimize or maximize x. So this one's going to move to the right because we have a positive value for our a value. So we're going to minimize x. We're going to look for the smallest value of x we can get. So what do I plug in for y to make this as small as possible? Well, it's hard to tell in this form. But if I divide everything by 3, and I complete the square. And of course, to do that, I'd have to have a plus 4 here. And then I move everything over to get x on its own. Timesing everything by 3, that's a 12 now. So when I subtract it, oh, here, I'll do this. If I times everything by 3, I get this. Again, times by 3, times by 3, times by 3, times by 3. Just trying to make this a little bit easier to subtract. When I subtract 12, I'll get x on its own. X is going to equal 3 times the quantity of y plus 2 squared minus 8. So what's going to make this x value as small as possible? Well, we know we can't make this any smaller than 0. We can't go negative. So what's going to make this 0? Well, when y is negative 2, that'll make this as small as possible. 0 minus 8 gives us our smallest x value, which is negative 8. So if I were to graph this, it's going to start at negative 8, negative 2. It's going to move to the right, and it's going to go 3 times faster than what it normally does. So negative 8, 1, 2, 3, 4, 5, 6, 7, 8, negative 2 is right here. And it's moving to the right. So I'll write my coordinate over here, negative 8, comma, negative 2. Negative 2, yep, negative 2. And again, it's going to move to the right, and it's going to move 3 times faster. So instead of 1 getting 1, 1's going to get 3. Instead of 2 getting 4, 2's going to get 4 times 3, which is 12. 4, 5, 6, 7, 8, 9, 10, 11, 12. And of course, it's symmetrical. If I go up 3, I'm supposed to go over 9, because 3 squared is 9, but it's going to move 3 times as fast. So up 3 is going to get me 3 times 9 in this direction, which is 27. And I don't have room for that. It's growing too quickly. So there's our parabola. Again, we know it's opening to the right because it's x equals. If we complete the square by removing our a value just for a second, so we can see easily what this needs to be. Moving everything back, we can tell where the bottom of this parabola is going to be. Far left, because it's opening positive direction. And our options are either right or left when we're dealing. What's going to make this as small as possible? Well, when y, and again, y, not x, because we're plugging in for y, when y is negative 2. We plug that in, we get 0 for everything. 0 minus 8 is negative 8. That's our smallest value of x. So that'll be the farthest left we go, which will be our vertex. We move up 3 times as fast in this direction. So instead of 1 getting 1 and 2 getting 4, 1's going to get 3, 2's going to get 12. Looking at 14.15. We want to find an equation whose graph is a parabola with vertex negative 2, 3. Well, let's just start right there. And a vertical axis of symmetry. So we know it's going to move up and down, because that's what a vertical axis of symmetry is. So it's going to be y equals. And we know if it's a parabola and it has a vertex at negative 2, 3, that means negative 2 for x. Whoops. When we plug in negative 2 for x, we'll get the smallest value we can in here. So if I plug in negative 2 for x, I'll get 0 for this. I know that, which is why I know I need a positive 2 here. Because again, I want to make this as small as possible to find that. And if this becomes 0, we're supposed to get 3 for y, right? When I plug in negative 2 for x, I should get 3 for y. Well, this is 0 when I plug it in right now. So in order to get 3 for y, I need a plus 3 here. And you might notice the connection between these numbers and what goes there. Right? Negative 2 is going to make it as small as possible, and then 3 will be left over. Now, the problem is that this is also supposed to be a solution to our problem. Not only should negative 2 get 3, but 1, when we plug it in for x, should get 4. Currently, this one does not get 4 when we plug in 1. If we plug in 1, we get 1 plus 2, which is 3. 3 squared is 9, and 9 plus 3 is not going to give us 4. So, like I said earlier, if we plug in 1, this whole thing becomes 9, right? When we plug in a 1 there, we get 3 squared. You wish that this was not 9, because 9 plus 3 isn't 4. Think about it. What plus 3 does give us the 4 we want for y? 1 plus 3. So you wish this 9 was really a 1. So what can I multiply by in the front with our a value so that the 9 becomes a 1? Well, the answer is 1/9. Because 1/9 times 9 gets us 1, and then we add 3 and we do get 4. So notice we haven't changed the vertex. The vertex is still -2 is going to zero this out, and we'll get 3 for y. But now we will get 4 when we plug in 1 for x. If I plug in 1, I get 3. 3 squared is 9. 9 times a ninth is 1. 1 plus 3 is 4. So it's a bit of a puzzle to figure out what goes here based on this point. Now for this next one, it's very similar. We have an equation whose graph goes through this vertex and goes through this point. However, it's a horizontal axis of symmetry. So it's going to move left to right. So that means it's going to be an x equals. So we're going to have y squared here for our completed square. And our vertex says that when I plug in 3 for y, so again, if I plug in 3 for y, not -2, 3 for y, I should get -2 for x. In other words, I should get the lowest possible value when I plug in -3. Well, of course, the lowest a squared thing could be is 0. So when I plug in 3, I'm supposed to get 0. So if I plug in 3 here, and if I have a -3 there, I will get 0. So because I have a 3 for y, I know I need a -3 there. Now, x is supposed to equal -2 when I plug in 3. Right now, when I plug in 3, I just get 0. That's cool. But in order to get -2, I need to subtract 2. So if I plug in 3, nothing, -2 does get me -2. So this is our vertex on our parabola. Problem is, as you might have guessed, it's not going to go through 1, 4 on its own. If I plug in 1 here, I get -2. -2 squared is 4. 4 minus 2 is 2. Ah, close, but not quite. So let's talk about that again. If I plug in 1 right now, I get 1 minus 3. 1 minus 3 is -2. When I square it, I get 4. So right now I'm getting 4 here. I wish when I plugged it in that I got 1 for x. So what minus 2? Let me cover up that square. What minus 2 gets me 1? For x, again, for x. 1 is x, not 4. Well, 3 minus 2 gets me 1. So I wish this were a 3 underneath here. So it's a 4 right now. Well, if I times it by 3/4, I'll get 3. Because 4 divided by 4 goes away. It's 1, right? And then we get 3. 1 times 3 is 3. So right now, if I were to plug in 1, I'd get 1 minus 3, which is -2. -2 squared is 4. 4 divided by 4 is 1. 1 times 3 is 3. 3 minus 2 is 1. And that's what we wanted for x when we plugged in 4 for y. Oh no. I goofed. I kept plugging in 1 for y. You've probably been screaming at home. It is very late. Let me try this again. We know this is right because of our vertex. We know that when we plug in 4 for y, we get 4 minus 3, which is 1. 1 squared is 1. 1 minus 2 is -1. Ah, close, but not quite. So again, when I plug in 4 for y, I get 1 here. 1 squared is 1. So I get 1 right now. I wish I was getting 1 for x. What minus 2 is 1? 3 minus 2 is 1. So I need this to be a 3. So right now I'm getting a 1. So if I times by 3, I win. Again, if I plug in 4 for y, I'll get 1 here. 1 times 3 is 3. 3 minus 2 is 1 for x. There we go. Part C. Is there an equation besides the ones we found here that does all the stuff we want, like go through 1, 4, and has a vertex at -2, 3? And the short answer is yes. There are infinite. 1 comma 4 is this. And -2, +3 is here. And that's our vertex. So we already found the equation that goes slowly up through 1, 4. That's this guy. Right? Of course it goes slowly because it's going 1/9 as fast as we normally would. And then we of course have this other equation that's moving right to left, and it's going 3 times as fast. So if I make it symmetric, you can see it's growing very quickly, right? But there are other equations that exist, not perfectly horizontal or perfectly vertical like these are, but are instead somewhere in the middle. Like you could do an equation that looks like this. That parabola goes through this point and has a vertex there. but it's just going diagonally, so it's kind of a mix between the two. An infinite number of equations exist that go through these 2 points. We just restricted ourselves to perfectly vertical and perfectly horizontal, which is why we only had these 2. So there will be others. But what are those equations? We'll do that another time. Do the circles. Ooh, nice. They're already completed the square. That's good. And we already know our radiuses, 2 and 5, right? Do they intersect when graphed on the same plane? Well, for this problem, there's lots of solutions, but the thing I would do first is I would just kind of graph them really quickly to see what's going on. I know our center is 2, 0, because when we plug in 2 for x and 0 for y, that's what makes this 0. And our radius is 2, the root of 4. So if I graph this, 2 zeros here, and if my radius is 2, I'm going to go out 2 in every direction. And now I've got my circle. And I missed this guy. There we go. Over here, my radius is -1, because that will make that 0, and 0 for this. And my radius, of course, is not 25, but 5. So if I graph this, at -1, 0 is my center, and my radius is 5. So if I go 5 in every direction, 5 in this direction, 5 in that direction, 5 in that direction, but more importantly, 5 in this direction, 1, 2, 3, 4, 5, I think you'll see where it intersects our other circle, right here. Just there. So it's going to intersect at 1, 2, 3, 4, 4, 0. This next one, it says, consider this equation. This is a circle. We don't know what the radius is, and we haven't got it in complete the square form, right? So we don't even know our center. But we know k is just some number over here. We want to know what's the smallest or biggest k can be so that we get a non-degenerate circle. And by non-degenerate, we mean it has a non-zero radius. Because imagine if a circle had 0 radius, right? Here's the center. 0 radius would just be a point. Or if it had a negative radius, which would be really bizarre, right? We like an inverted circle. So we want a non-degenerate circle. In other words, we want a radius that's bigger than 0. So let's first figure out what our radius is based on this information and figure out where our center is. Well, if I complete the square, I'm going to get x minus 2 quantity squared. And I'll need a plus 4 to make that happen. I'll also get plus quantity of y plus 3 quantity squared. And I'll need a plus 9 to make that happen. So what I'll really have when I get it into vertex form, or I guess center form for our circle, is this. So in other words, I've got k plus 13. Remember we said that our radius, which is basically this, needs to be non-zero, and it can't be negative. So k could be 1, because that'd make it 14, right? That's totally fine. K could be 2, k could be 3, 4, 5, 6, 7, 8, any number that we want as long as it's positive. But what about negative numbers? Well, -1's fine, because -1 plus 13 is 12, and that's bigger than 0. If we go down to -13, though, -13 plus 13 is 0, so that's when we get a 0 radius circle, and we don't want that. So k definitely can't go below 13. In fact, it can't even go to 13. It has to be bigger than -13. Anything bigger than -13 will make this positive. Anything equal to -13 or smaller will make it negative or 0, which is a problem. So based on this, we know k has to be greater than -13. Otherwise, we'll get that non-degenerate circle, or a degenerate circle, I should say, which is not what we want. We want a non-degenerate circle, a circle that does not have a negative radius and doesn't have a 0 radius. Again, plugging in values of k that are bigger than -13, like -12, -11, +6, all of those will lead to something that isn't negative or 0 here. So anything bigger than -13 will work. 1424 talks about what a diameter is, but I think you know what a diameter is. It's saying our diameter is made up of these endpoints. -5, 0, and 25, 0. Well, the diameter gives us the radius, right? If we cut it in half. So how long is our diameter? Looks like from -5 to 25, we have a diameter of 30, which means our radius is 15. Well, where's our center? Well, if we go 15 away from any of our points on our circle, and these are both points on our circle, we'll find our center. So if I go 15 away from this, I end up at 10, comma 0. Same thing if I go 15 to the right from here, right? So here's our center. It's not on the circle, but it is our center. If we go 15 up, we get this point, 10 comma 15. That's on our circle. And if we go down, we get 10 comma negative 15, which is also on our circle. So their question is if the point x comma 15 is on our circle, then what is x? Well, we know what x has to be when y is 15. When y is 15, x has to be 10. Directly above our center, right? Because it's gone 15 off the x-axis. So it has to be directly above our center because we're maximizing our radius here. So x will be 10. And that is the last of the intermediate problems. So what I'm going to do now is I'm going to stop talking, stop recording, and I'm going to upload this so you can see this as soon as possible. Hopefully it gets to you in time where you can use this either before you have my class tomorrow, or actually you have your final on Friday. So hopefully it'll be okay. I'm talking to Abbi here. Emmalee, of course, has a first hour now, so I need to get this out ASAP. Sorry for the delay.